Hello everyone, this is Dilleswara Rao from Aeronautical department. So today I'm discussing on stability augmentation system on our series of automatic control of aircraft lectures. So last few classes we have discussed on autopilot system, displacement autopilot system, and pitch orientation system, acceleration orientation system also we have discussed. So like after that, we have given some introduction on Laplace transform solution and transform function solution also we have just discussed. So if you remember that, you can have a look on that. So here we are going to discuss now on this stability augmentation system. So stability augmentation system is these will be generally discussed on what are the control surfaces we have. That control surfaces, how it has been augmented for better performance, and what are the significance of the control system perturbations and small changes on the control systems also, how we can design, and what are the things involved on that one also we will be see it on this module. So let's go into the topic. So here the stability augmentation, like generally for a maneuvering of aircraft, like every aircraft will be the commands will be determined by the speed of that rotational modes only. Like rotational modes mean not only like rolling or pitching movement. So general like forward movement or rolling movement or yawing movement or pull up, pull down, these type of moving commands. So generally, that will be depends on the speed of the aircraft. So the frequencies of these modes, like this modes means for generally whatever the displacement, displacement happened on that aircraft. Like displacement means what? Whenever it is going forward, also that will be a displacement, and moving, rolling. Rolling movement and the pitching movement and yawing movement and pull up, pull down, steep turning also. These are all comes under displacement of aircraft only. So when these displacements, generally in mechanics we call it as a mode shapes. Mode shapes means that will gives you that behavior of that displacement. So here also these modes of displacement of aircraft can be sufficiently high at height that the pilot could find the difficult or impossible to control the aircraft if modes are very lightly dampened or unstable. Like whenever these type of movements for an aircraft have been given by pilot is general in general it will every movement previous classes we said like whenever we give a displacement to that control surface, that control surface will generate a frequency response. I mean, frequency response means the damping to that aircraft, or the whole aircraft will react to that control surface movement. Due to that movement, what will happen? The aircraft will be having lot of displacement. I mean, lot of vibration. Like not we can say like a vibration. So it will be like a moving up and down, or maybe like a spiral way movement. Also, generally it will have. So due to that frequency response, we need to give that control surface signal in such a way that it should be control. I mean, it should be in control of pilot only. Otherwise, if the pilot loses his control on that controlling the aircraft, so the aircraft will go to that unstable condition only. So again, that will be another criteria. So here you see the necessity to provide the automatic control system, like here. So for avoiding this suitable dampings and natural frequencies, I mean, to compensate the natural frequencies. So the control system required for avoiding these type of perturbations are called as a stability augmentation system. If that augmentation is intended to control the modes and provide pilot to particular types of response to that control inputs, then that is called control augmentation system. Like you say, when we are giving a control, when we are tending to move that aircraft, like a pilot tending to move that aircraft, so that aircraft can withstand its natural frequencies and dampings. I mean, it will avoid that dampings, and it will regain its stable position within a short period of time. So for that, for making that system stable, whenever we are giving whenever we are giving deflection to the control system, even though the aircraft can able to come to its original stable condition, so that required system is called as a stability augmentation system. And if the control systems, if the control system responses also coming to that original neutral position, then that type of system is called as a control augmentation system. Like here we are giving that the aircraft tending to come to its original position or stable position. So the stability augmentation system main requirement is to make that aircraft to stable, or if it is making an if it is moving on differential unstable condition also, it can regain its stable condition. So this augmentation system will help the aircraft to regain its stable condition. So likewise for control surfaces also, if the system can able to regain its neutral position of that control system, is called it as a control augmentation system. That means this is helping that whole system to make it stable. Or ultimately, our goal is what? Our goal is need to be stable that aircraft only. For a stable condition of that aircraft only, we are all want this type of systems only. But you can ask me, like every system, every control system, like previously we said that pitch control, pitch orientation, displacement, autopilot system, these are all required for making that system into stable only. But even though there are like, I mean, in the displacement autopilot system and the pitch orientation system, if you see, when you're giving that system signal in terms of voltage or in terms of control stick input, it is getting it is getting moving in a unvariable condition only, like uneven conditions only, that aircraft is tending to move. If you see that frequency responses diagram and that damping diagram also, that is not for just a graph purpose. That is giving that aircraft can move like that only. So that graphs are giving you information like a whole aircraft can have a frequency like that. I mean, frequency means whole aircraft can vibrate like that. But here, this system can avoid that vibration. Like the system is used to avoid that vibration and making that system into stable condition. I mean, it will make that system came back into the stable condition. So that type of system is generally called as a stability augmentation system. Okay. So that the high performance of commercial and military aircraft will not meet the flying requirements without this stability augmentation system. So some of the aircrafts are actually unstable and would be impossible to fly without an automatic control system also. Like if it is not there, then we can't even control that aircraft also. So this SCS typically uses sensors to measure the body axis angular rates and rates of the vehicle, and feedback processed versions of these signals to the servo mechanisms, and that drives the aerodynamic control surfaces also. Like servo mechanisms will gives you the input to that control systems only. So in this way, like aerodynamic movement is proportional to the angular velocity, and its derivatives can be generated, and using the these are used for producing the damping of that motion only, damping effect of motion only. So generally, this mode shape is unstable, or if it is desired to change both damping and natural frequency independently, then additional feedback signals are required. Like whenever whenever we are giving control input to that control system, so that it will be unstable only. Like when we are giving control input to that control system means it will move so that the whole aircraft will go to some unstable condition. So if it is moving to the unstable condition, that pilot can feel that unstable condition, and he has to made his efforts to bring back to stable condition. So for that, feedback systems also required. So same as in this automatic control system also, feedback systems are required for making that control systems to move and regain its original condition also. So that stability augmentation systems are generally designed separately for longitudinal dynamics and lateral and directional dynamics controls also. These SAS systems are generally designed. So in this first we will talk about pitch axis stability augmentation. So this pitch axis stability augmentation system is it will gives you the satisfactory neutral natural frequency and damping of short period mode. So like it will gives you the satisfactory results on applying results on making it in a short period approximation mode, and this will involves on variables alpha and variable alpha and pitch rate, so that feedback of these variables to that elevator control will modify the frequency and damping, so that figured mode will be largely unaffected by this feedback. Like figured mode means what? So whenever this frequency response is turns into that figured mode, so the pitch rate and alpha, the variables of alpha can be useful to that elevator control. Like that elevator control can be easily modified, and it will be making it into a stable condition without any external feedback loop. So inner feedback loop only will gives you that control system to be more precious and to be more stable when we are operating that system. So these feedback loops will often be closed around the pitch essays to provide autopilot functions or pilot controls for example, normal and acceleration. Like whenever these feedback loops will be like a closed feedback loops only. So this will gives you like a autopilot. This will serves as an autopilot system, and this will gives you that pitch control. Controlling of that pitching moment. Like in whenever it is in acceleration condition, or maybe in the z-axis movement orientation also, we can control with this one. So that automatic adjustment of this augmentation, like that inner loop feedback gains may be arranged when the outer feedback loops are engaged, so that that overall performance will be optimal. Like we know that inner loop feedback system is being introduced for the pitch orientation system and displacement autopilot system. If you see that feedback system, why we are introducing that one? So that one because of onboard. That instant feedback system will gives you that proper control system, like a proper controlling of that control surface, and so that that whole system will be in stable condition, and the frequency responses will be not in over damped condition. So it will be in the frequency response will be in will be under under controlled atmosphere only. So here you see the block diagram of this sales system. So that the feedback of alpha and pitch rate for controlling of short period mode. So see here that block diagram of the system. So here there are two feedback systems have been connected to this summer only. Again, this is a summer only. So this is an integrator, and this is an aircraft control surface control surface system. So here there are this is alpha feedback system, and this is pitch rate like a pitch rate feedback system. So this pitch rate feedback system and alpha feedback system has been again summing to this transfer function, so that the feedback will be very precisely, it will control that controlling input, so that the output signal will be very refined, and it will be under control whenever if it is having in unstable condition. Also automatically it will regain the stable conditions by changing this by changing the instantaneous changes on these feedback loops. So here that the transfer function G, like here you see that GA is there, no? The transfer function G represents the elevator actuator, or complete closed loop elevator servo. Like this is a elevator actuator transfer function only. So, and the transformation function G, is the noise filter used to low pass filter and angle of attack signal only. Like here that the G function will gives you, like here the G feedback function is there, no? The G feedback function and G function will gives you that elevator servo control, and that noise filter and the low pass filter, and low pass filter to that angle of attack signal also it will be compensate. So if the short period mode is lightly damped, otherwise adequate, so only pitch rate feedback is required, and pilot comments will be applied to that input only. Like if that short period mode, like whenever this transfer function is operating at the short period mode, so only that pitch rate feedback is required. Like for that pitch rate feedback is required, then the pilot commands will be the pilot commands will be depends on this pitch rate pitch rate feedback system only. If frequency and damping both are unsatisfactory, that means that mode is more unstable, so that alpha feedback is necessary, and that integrator outer loop feedback will be compensate according to this one. Like only pitch rate feedback system is required, so that this will be nullified, and that control system signal will be depend on this feedback system only. But if frequency and damping both are getting unsatisfactory results, like whenever it is going to unstable condition, and that damping and frequency ranges are going to going beyond the design values, so that it will take this alpha feedback system signal also, then it will compensate that summer signal to that transfer function, then it so that it will make that system into stable condition. So that if you see, that pitch rate sensor is normally a mechanical gyroscope device. Like here you see that pitch rate sensor is there, no? So this is normally a gyroscopic device. So, and it measures the absolute angular rate about the sensitive axis. Like whenever this gyroscope device is involved, then what it will be? It will be very accurately. It will measure that movement. Like if you want to just move like some 2 degrees pitch only you require. So for that 2 degrees pitch, accurately measure that value and gives that feedback to that summer, so that that summer will automatically cut off the signal, and that pilot can get the feedback from the control system, so that yes, we can stop our control, and we need to move. After that only we need to move forward. So a setup for 3 orthogonal gyros is used to measure the angular rates around the aircraft body axis. So that the location of this gyros must be chosen very carefully to avoid the picking up of vibrations of aircraft. Like these gyros should be selected very accurately, because see here, the total control system is being depending on that gyro feedback only. So that gyros should be very carefully we need to select. And an ideal structural oscillation. So at a node, that angular motion but no displacement, like only angular motion is there but no displacement is there. Then at an anti-node, that converse is true. Thus the first choice for the rate gyro location is an anti-node corresponding to most important structural mode. So like you see, for a structural oscillation, here the first choice for rate gyro location is antinode corresponding to its most important structural mode only. Then the flight test, like a flight test must be then used to adjust the position of the gyros. A bad choice of gyros, like whenever if you are not careful on selecting this gyros, so adversely affect the flying qualities, and extreme cases cause oscillations in flight control systems also. Like for example, one of the system, one of the reference we have seen here. This is a case study report only, 1984. Some degrees of fluttering of gyro output will normally be required. Like whenever if you are, if you are not choosing a good gyro system for making this control system, so there will be extreme or oscillations will be extreme oscillation will occur on a control system, as well as it will flutter the gyros input also, and the control system vibration also very uneven in nature. Okay, so that alpha sensor, like another thing is what alpha sensor. So that alpha sensor may be like a pressure probes or a small wind vane mounted on the side of the aircraft body, and position to measure the alpha over a wide range of flight conditions. Like this alpha sensor is a like a pressure probe. Like a pressure probe means not like it will measure the pressure. Like pressure probe means it is sensing that it is sensing that movement effect. Like whenever if you are giving that small angle of attack, due to the small angle of attack, like a small angle of attack, if you give like this, so for that movement, it will sense that movement very rapidly, like very precisely. It will sense that movement and will gives you that feedback to that. So it's like a pressure probe only. So it will act like a pressure probe, and that aircraft body and positioned to measure the alpha over a wide range of conditions, like yeah, so that it will measure that total flight orientation with respect to that flow condition, and it will measure that it will measure that position also very accurately. So these two sensors will be used used on opposite sides of aircraft to provide the redundancy and possibility to average the out measurement errors caused by side slipping. So a true angle of attack must usually be computed from the indicated angle of attack. This angle of attacks will be computed from indicated angle of attack, airspeed and Mach number in order to relocate the free stream angle of attack of the airframe to that direction of flow field at the sensor's position. Like the true angle of attack, generally the true angle of attack where we will measure from the indicated angle of attack system only. That the indicated angle of attack of airspeed and Mach number in order to relate the free stream angle of attack of airframe to that direction of flow at direction of flow, we will get the sensor position only. Like where the sensor position is accurately showing, so there only we will see that total angle of attack, like a true angle of attack, the true angle of attack for aircraft. So the signal from alpha sensor is often very noisy due to turbulence, and noise filter reduces the amount of noise injected to that control system, because whenever it is getting moved and it is getting pitching up, so that the air velocity will be very high near to that sensor. So due to that, too much of noise will be produced, and that due to the turbulence also, like whenever like you see when an airfoil is like that, and if it is this is a free stream condition, so if it is getting changing according to this orientation, so due to this orientation, if this orientation, if it is changed to this orientation, suddenly here the wake region, displacement will be very high, that flow deflection will be very high. So here the velocity will be automatically high only. So due to this high velocity, that noise production also very high. So that higher turbulence, that because of sudden turbulence also, that noise will be produced very high. So that system will be noise filter system is required to take out that noise from that sensor also. So that alpha feedback is avoided if the this feedback is avoided if only because of difficulty of getting accurate noise-free measurement, and because of that vulnerability of sensor to mechanical damage. Like this feedback generally we can avoid whenever, I mean it is not we cannot avoid this feedback, but whenever that noise-free measurement and that sensor mechanical damage, if you want to avoid, so that if you want to avoid that, so that this alpha feedback can be avoided. So the noise from alpha sensor can make it difficult to achieve the precise pointing, like due to that noise produced by this sensor. So that positioning pointing is very difficult. So the amount of alpha feedback is very, normally restricted. So we shall see, if it is eliminated completely when the basic aircraft dynamics are stable. Like, because we said no, the pitch rate system and alpha system. So that alpha sensor system is we need to avoid so that that noise can be filtered. So if you want to avoid that one, we need to make that system stable. We need to see that system should be stable. Then only we can totally eliminate that alpha sensor feedback only. So here you see that longitudinal the Jacobian matrix, like this is the A matrix. If you remember that A matrix from that previous longitudinal equation of motion, Laplace transformation of that differential equation. So from that differential equation, we have got the values for velocity, angle of attack, that pitch rate, and elevator angle. So these values we can get that differential equation solution only from that solution only. So see here, for the B and C matrix also we will get this value. So that the single input of the elevator deflection delta in the degrees, and the two outputs are appropriate feedback signal, like alpha and pitch rate. So this is alpha, and this is pitch rate. And the entries in the C matrix are conversion of units in degrees only for consistency of aircraft. Like these values are the conversion units only. So either of two SASU transformation functions from the coefficient matrix will be exhibit the dynamic modes of flight condition only, so that that elevator to alpha transfer function will be changed to like this. So that elevator to alpha transfer function will be like what? So minus 0.121123 into s plus 75 into s plus 0.0098 plus or minus j into 0.09379 by s minus 0.97 into s plus 1.912 into s plus 0.1507 plus or minus say j 0.11. So this transfer function, how we got from that previous by using this matrix only. If you see that Laplace transform solution you can get how by using this matrix how we will get the transfer function in terms of imaginary axis and Laplace operator. So unlike that transfer function, like a stable CG position, so the transfer function does not exhibit the unusual phogoid and short period poles. So if the pole is at 1, S is at 0.1, indicates the unstable exponential mode with a time constant of 10 seconds. If the complex conjugate pole pair corresponding to an oscillatory mode with a period of 33 seconds, and the damping ratio will be 0.79. So if you get these values, we will get from the previous equation solution only. So this is like a phogoid mode with a short period damping ratio. Like the damping ratio we are getting 0.79, and this oscillatory mode will be like 33 seconds only. So this combination we can write it like a phugoid mode with a short period damping ratio. This mode is the third oscillatory mode of that statically unstable airplane. This is like a third oscillatory motion. While we are giving the input to that control system, we are getting that oscillatory period oscillation for a period of 33 seconds with a damping ratio of 0.79. So this type of values, if we are getting with this transfer function, so that this type of this mode is called a third oscillatory mode. So the modes described above, previously, do not satisfy the requirements of good handling qualities. So, providing continuous control of the unstable mode would be very demanding job for a pilot. This is, you see here, 33 seconds that oscillatory motions have been acquired on that control system. So these type of long period oscillations are mostly avoided. It should be avoided. So otherwise, here you see the aircraft is unstable condition for 33 seconds. So for more than half of a minute, the aircraft is in unstable condition. So if it is that much, if the aircraft is in that much level unstable condition, so it is, it's very hard to make it into that stable condition. So the pilot should avoid this operational condition. So the pitch SCS can be designed to restore this conventional short period and essential for this airplane. So the explanation of this unstable mode can be traced where the conditions of positive pitch stiffness will be described. So that F-16, for an F-16 pitching moment, for an F-16 fighter, the pitching moment curve has been a positive slope over some ranges of alpha, and the model is statically unstable in these regions, so which leads to unstable dynamic mode only. So this provides an additional clue that the type of feedback needed here is to stabilize the unstable mode and that angle of attack also. Like here, that feedback system is required in such a way that it has to avoid this unstable mode of angle of attack. So the derivations from the trim angle of attack attacks are sensed, and the feedback to the elevator servo to generate a restoring pitching moment. The slope of the pitching moment curve can be made negative in the region around the trim. Like if the derivatives of trim angle of attack, like a trim angle of attack derivative, stability derivative, you see that stability derivatives are sends the feedback to that elevator servo to generate a restoring pitching moment. That pitching moment, if the pitching moment is restored, so that slope of the pitching moment curve can be made negative, and it will be in the region around that trimming condition only. The short period mode will be then stable. Furthermore, that overall pitching moment curve will be trimmed in elevator reflection, and it will not be affected. So that thus the preserving the trim drag and the maneuverability characteristics that the designer has to build that basic airplane design. That a basic airplane design needs to be taken care of needs to taken care of these conditions also. The trim angle of attack loses the meaning of aircraft maneuvers. In order to make this scheme work, so a way must be found to compute the alpha reference signal continuously. Here we said, when we are making that pitch rate feedback only, when we are considering only that pitch rate condition, so that the control system is having this much of frequency response. So here what we need to do, that if alpha sensor signal also we need to be compute continuously. So on this way, the alpha reference may be provided automatically, is to include a integrator in the control loops, so that loop can be arranged so that if the pilot commands inputs have been satisfied, there is no input to that integrator, and that output remain constant at a value that corresponds to reference of angle of attack only. Like if that loops are arranged, these feedback loops are there, no? If that loops are arranged in such a way that that pilot have been satisfied with that integrator input only. While we are giving that input to that integrator, that integrator input itself satisfy that control surface movement, and it is not based on that alpha sensor feedback, and it is only sensing on that reference of angle of attack only. Sorry, if that integrator of, let's say, airport output is remain constant at a value corresponding to that angle of attack reference only, so then that system will be stable, more stable in condition, and we can avoid that uneven vibration to that system also. So this way, I mean, in this way, you can say like that stability augmentation system, depending on this pitch rate sensors and alpha feedback sensors also, how it has, how these are, I mean, how these are significant for making this control system to be stable, and why these systems have been used to make the system more stable. Also, we can see this. So in the, I mean, in the coming classes, we will see another system also. So that is a pitch rate. We'll see that roll rate. Roll rate feedback also we will see, and lateral dynamics also we will see it on coming classes. So that's all about this stability augmentation system part one. So in the part two, in the coming lecture in part two, we'll discuss further more examples with pitch rate feedback sensors and roll rate feedback sensors also, and how that systems have been significant to make this system stable, and how to avoid further delay in the feedback system, and make how to make this control system so much stable for giving that output in a very precise condition also. We will see it on coming classes. So that's all about this one. So you can refer that this textbook for making this control system augmentation and stability augmentation system, and previously we said Laplace transform systems solution also you can get it from these books, and other furthermore references you can refer these books also. Okay, so that's all about this one. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.